Okay, hello everybody. Welcome to the last session for 2 days on 4th IPM Advanced School on Computing. I'm honored to introduce Dr. Sara Sabour. She will be presenting Capsule Networks. Sara Sabour is a research scientist at Google Brain. She has done her graduate studies under supervision of Professor Fleet at University of Toronto. Prior to that, she graduated from Sharif University of Technology. Sara's research interests are focused on machine learning and computer science. Most notably, she and Professor Hinton have been working on a next generation of neural networks called capsule networks. Their work has been reviewed by several media outlets, including a New York Times article. So please watch the video, record the session, and we will be back in half an hour for Q&A session.
Hi, my name is Sara Sabour. I will be presenting an introductory talk in a series of talks on capsules and capsule networks. There is a QR code on all the slides for asking questions. Please feel free to post your questions during the talk. I will be answering posted questions after the talk. This talk will be approximately 40 minutes. This is not a literature review. I will review our motivation behind our research on capsules. I will introduce a basic elements of capsule networks and discuss 3 variations of capsule networks. These basics will be useful to anyone interested in applying capsule networks in new domains. We will have a survey of recent developments in the next session. So let's just start with a challenge. This is for you, the audience, to solve. Take a moment to look at these 9 pictures. In 5 seconds, you are asked to draw all of them from memory as accurately as possible. Just memorize them to be able to draw. Patterns. Did anyone figure out any distinctive and shared patterns across all 9 examples? In fact, there are groups of points in the shape of squares and triangles. On this slide, colors are used to highlight these patterns. By the end of this tutorial, we will learn about a system that can find such patterns. It can efficiently reconstruct the input, and it is unsupervised. Occlusion. Occlusion is a computer vision challenge that is beyond simple pattern matching. Consider the following task that involves occlusion. Similar to MNIST, the task is digit classification. However, instead of 1, we have exactly 2 digits overlaid. The task is to predict the class of both digits. The ground truth label is shown underneath each image. For example, the first image on the left is a 5 and a 9 overlaid on each other. This is our second task, and capsule networks perform significantly well on this. The third computer vision challenge we consider is Viewpoint. Capsule networks also work well facing the challenge of viewpoint. Suppose we want to classify objects. At training time, we only get a front view of the object. But at test time, the image can be from any viewpoint. Capsule networks can also help us to generalize to new viewpoints. So let's start with a question. Suppose we call this picture a house. Then we can also call these 2 pictures houses. They're slightly transformed, but still the same general look. But if you separate parts from the whole and mix them randomly, it is no longer a house. No one calls these images a house. So what we essentially want is a system that is viewpoint equivariant at all levels. A system is viewpoint equivariant if any viewpoint change in the input results in a similar viewpoint change in the output. So CNNs, without a stride and pooling, are translation equivariant, but not viewpoint equivariant. They replicate the computation over the grid of pixel positions equally, and if you move the house around in our example, it will not hurt the CNN much. But if you change the viewpoint of the camera, CNNs do suffer. So should we stick to CNNs and read all degrees of freedom in the viewpoint as well? Or should we find new basis functions and replicate filters on computations in a new basis? Our proposed solution is not but capsule networks. As we discussed in these pictures, viewpoint is varying. But what is staying constant? What is left of the house when we remove the viewpoint? The answer of computer graphics is to go beyond pixel space into vector space. So put a coordinate frame on all the detectable objects, houses, roofs, walls, anything that you detect. Now look for the constant again. Can you see it? Take any roof in these pictures. Regardless of its coordinate frame, if you rotate it by 90 degrees and scale it a little, you can get the coordinate frame of the house. Basically, we can find the coordinate frame of the house from the roof from any viewpoint. We just need to know the coordinate frame of the roof and the relation between the coordinate frame, and we can get the coordinate frame of the house out of that. But the big question is, what is a coordinate frame? The coordinate frame should encode information about the viewpoint, like rotation and scale. So suppose I ask you to put coordinate frames on this chart and its parts. Here's one way you could do this. I'm arguing that the choice is arbitrary, but coordinate frame of parts have to be consistent with each other. The coordinate frames are multidimensional, obviously. So what we need to learn is the relationship between two coordinate frames. We will represent this relationship using a single matrix. Usually, we only carry around the information that something exists. But now, in addition to that, we want to also carry how it exists. So we introduce a new concept, capsule. From now on, we call a group of neurons about a single entity a capsule. A capsule shows both whether an entity exists and how it exists. It can be just 6 neurons together viewed as a vector, or 17 neurons together like that, or 9 neurons together viewed as a matrix. The core concept is that it should be all semantically grouped to each other. So we have figured out the constant and variable parts of a house representation. In the house example, we will represent the roof using a capsule and the house using another capsule. And we will learn to find a transformation from the roof capsule to the house capsule. But how can we detect objects? Is any roof a house? No. A house needs walls. So a house exists if it has both roof and walls. Suppose we know how to transform a roof capsule to a house capsule. We also know how to transform a wall capsule to a house capsule. But the house capsule should only be activated if and only if the transformation matches between the roof capsule and the wall capsule prediction. In other words, roof capsule and the wall capsule should agree on their prediction for the house so that the house exists. To learn more about this concept of agreement, consider a digit classification task like MNIST. We propose a model with the following architecture. The model consists of 3 layers. The first layer of capsule consists of 7 parts, shown on the bottom row. Each of these capsules will find their individual coordinate frames about how these patches are present in the image. First layer capsules with 7 parts are connected to the second layer capsules, consisting of 12 capsules. Second layer capsules will be responsible for detecting higher level. Second layer capsules will be responsible for detecting higher level conceptual parts, such as the image on the right, or this one, or something like that. So assume that you have a model that can detect these 7 parts and fill the first layer with the coordinate frame. Each first layer capsule transforms their coordinate frames and sends 7 predictions to each mid-level capsule. But not all predictions on the first layer capsule belong to all the mid-level capsules. For example, in the digit 3, some active lower capsules will belong to the red capsule shown as the top right part of the tree, and only to that part, while some of the other active capsules in the bottom belong to the other higher level parts of the tree, shown as the red capsule again. This means in order to find an agreement, we need to find a scene parse tree. Given a parse tree for a scene, each capsule will get a parent and it will send its prediction only to its parent. A capsule with no child is turned off, so assigning parents is a layer-wise nonlinearity because parents compete with each other. This is substantially different from between capsule networks and traditional convolutional neural networks. In each layer of a capsule network, groups of neurons compete to find supporting parts, and within groups, neurons cooperate to activate a part. In what follows, I will discuss 3 approaches to finding agreement and assignment between capsules. This will be using dot products, using expectation maximization, and using mixture models. But first, let's see a complete architecture of a capsule network by connecting capsules to images and training them up. We connect the image to the first layer of capsules with a convolutional layer. And now all the coordinate frames get transformed into first capsule layer parts. These transformations are the only chainable parameters between 2 consecutive capsule layers. So now we get these transformed coordinate frames, and given a set of them, do these agree with each other or not? So that's the question now. To figure that out, we call this nonlinearity agreements and assignments. If the child predictions agree, the parent capsule gets activated. The parent capsule gets the agreement as its coordinate frame. Last capsule layer predicts the existence of classes, and the classification loss is used to train the network. Now let's dig into the agreement and assignment functions. The simplest method is using the cosine distance as the measure of agreement. Then set the norm of the coordinate frame to the existence probability of the capsule. This was introduced in a joint work with Nick and Jeff presented at NORIP 2017. Question is, why does this work? So let's illustrate each capsule. The orientation of the vector represents the coordinate frame, and the length of the vector represents the probability of existence. Consider the following two cases. In the first case, the top half of the figure, the vectors have the same orientation. In the second case, the bottom half of the figure, the vectors do not align. What does the sum of these vectors look like? The length of the summed vector will be large if their orientation agree, and only in that case. To keep the lengths as proper probabilities, we renormalize the norm and squash them below 1. So summing the prediction and squashing them gives the next capsule with an agreed orientation and length below 1. So we have found a way to do the agreement. But how can we do the assignments to refine these agreements? So now we want to boost the agreements by assigning parents. We use a ransack style refinement. Take these 5 capsules depicted as vectors, transform them into predictions for each of the 3 capsules in the next layer. Then sum the predictors, and this is the initial guess for the next layer capsules that we have so far. Now, orientation was our indication of coordinate frames. So, in order to measure the agreement, we measure the who belongs to who. We take the dot product of each prediction with the new capsule coordinate frame guess. Choose the one with maximum dot product as parent of the blue capsule. Remove blue predictions for the other 2. All the 5 lower level capsules choose their parents this way based on the dot product of the predictions with the next level capsule. So we remove the predictions for the non-parent capsules, and after assignment, recalculate the sum. Since now there is fewer outliers, the next layer capsules get boosted. This is a demo showing how after 10 routing iterations, capsules converge to a parent assignment. Here we show at the bottom level capsules with red circles and top level capsules with blue circles. At iteration 1, all red capsules send a prediction to each blue capsule. Then they select soft parents based on their cosine similarity. Iteration 2 of the nonlinearity, the connections get sparser. In practice, using 3 iterations gives enough assignments, and we don't do like all the 10 iterations. So now let's consider the clutter task to illustrate the power of dynamic routing. This is the similar task to MNIST for classifying digits, but now there are 2 digits in each image overlaid. The top images show samples of the input image. The ground truth labels are shown beneath each column. Capsule networks have significantly better accuracy than baseline CNNs in classifying these images. But the capsule network has coordinate frames in addition to their existence. So we further investigate their performance by training a decoder on top of the coordinate frames. On the bottom, we overlay the reconstructed images from the 2 most active capsules. We see the 2 most active capsules. We see that if a pixel belongs to only 1 digit, it will only get reconstructed 2 most active capsules. We see that if a pixel belongs to only 1 digit, it will only get reconstructed using that digit's coordinate frames. So let's take a closer look at these 2 examples. At the top left, we see an image of overlaid 9 and 5. At the top right, it's the 7 and a 1. The reconstructions at the bottom are from the 16-dimensional coordinate frame. Obviously, they are good, but not perfect image of overlaid 9 and 5. At the top right, it's the 7 and a 1. The reconstructions at the bottom are from the 16-dimensional coordinate frame. Obviously, they are good, but not perfect. Looking at the corners, we see evidence of proper seam parsing. To explain the small tip at the corners, we see evidence of proper seam parsing. To explain the small tip at the corners, it does not thicken the other digits as it is customary with CNNs to minimize the error. Since the notch does not agree with the parts of the other digit, it is not reconstructed from both coordinate frames. So one reconstruction of one coordinate frame is green, the other one is shown in red, and when they overlap, it is not reconstructed from both coordinate frames. So one reconstruction of one coordinate frame is green, the other one is shown in red, and when they overlap, it becomes yellow. So if something is only red or if it's only green, then this belongs to only one of the capsules. We want to evaluate only green, then this belongs to only one of the. We want to evaluate CapsNet's viewpoint generalization as well. So after chaining on MNIST viewpoint generalization as well. So after chaining on MNIST digits, we test them on affine transformed MNIST test digits. Capsules show significantly better viewpoint generalization than baseline CNNs. But using the norm as the measure of existence is problematic. If a coordinate frame is scaled, it should have a larger norm as well. So we need to find a way to represent existence separate from the full significantly better viewpoint generalization than baseline CNNs. But using the norm as the measure of existence is problematic. If a coordinate frame is scaled, it should have a larger norm as well. So we need to find a way to represent existence separate from the full dimensional capsule representation. So far, the length of the coordinate frame was an indicator of existence. In the slide, we visualize the capsules with arrows of as well. So we need to find a way to represent existence separate from the full dimensional capsule representation. So far, the length of the coordinate frame was an indicator of existence. In the slide, we visualize the capsules with arrows of different lengths so far. Now that each capsule has a indicator of existence. In the slide, we visualize the capsules with arrows of different lengths so far. Now that each capsule has a separate existence, we will visualize them with circles with different radiuses. The position of the circle shows the capsule coordinate frame, and the radius shows their existence probability. So how do we find argument and assignment when existence is separated from the position of the circle shows the capsule coordinate frame, and the radius shows their existence probability. So how do we find argument and assignment when existence is separated from the coordinate frame? Consider the 10 low-level capsules visualized on the left with different existence probabilities and coordinate frames. From the 10 active capsules in the lower on the left, with different existence probabilities and coordinate frames. From the 10 active capsules in the lower level, we want to figure out the next level 3 capsules on the right. First, as always, we compute the predictions by transforming the coordinate frame. Note that these transformations are the only trainable parameters. They are learned by optimizing the classification laws on the existence probability of the class capsules at the end. Previously, we had transforming the coordinate frame. Note that these transformations are the only trainable parameters. They are learned by optimizing the classification laws on the existence probability of the class capsules at the end. Previously, we had cosine distance as a measure of agreement. Now, the norm is part of the coordinate frame. So, we use Euclidean distance as a measure of agreement. If the predicted coordinate frames agree with each other, then they form a... Now, the norm is part of the coordinate frame. So, we use Euclidean distance as a measure of agreement. If the predicted coordinate frames agree with each other, then they form a cluster. So we fit 3 Gaussians to find the agreement. We find the center of Gaussians by averaging the points. This is similar to the maximization step in expectation maximization algorithm. The black disks show the Gaussians we get for each set. The center of the Gaussians 3 Gaussians to find the agreement. We find the center of Gaussians by averaging the points. This is similar to the maximization step in expectation maximization algorithm. The black disks show the Gaussians we get for each set. The center of the Gaussians are the coordinate frames of the new capsules. On the right, we show the 3 new capsules. To refine the capsules, we perform a parent assignment step. This is similar to the expectation step in the EM algorithm. We choose parents expectation step in the EM algorithm. We choose parents based on which Gaussians explain which lower level capsules by EM algorithm. We choose parents based on which Gaussians explain which lower level capsules best. On the probability under each Gaussian. So we have removed some of the predictions based on who explains who best, found the assignment, and then we run the MS step again, or do an agreement. Then we refit the Gaussians with a maximization step. We recalculate the weighted average to find mean and standard deviation of the Gaussian. The capsule exists if its Gaussian is tight with several points assigned to it. The Gaussian with large standard deviation or few children gets deactivated, like the new green capsule at the bottom. A tight cluster, like the new red one, is an active capsule. Center of the clusters are coordinate frames of new capsules. So the coordinate frames are the centers of the clusters, and the tightness of the clusters indicate whether the capsule exists or not. Let's take a look at how the assignment changes in practice for real images. This experiment is on NORP dataset. Take the image on the right. We want to classify it into one of the 5 classes: animal, human, plane, truck, car. So here we are showing the number of predictions near the center of each of the 5 final layer capsules. At iteration 1, there are some predictions for all capsules near their centers. So all the 5 capsules are semi-active. At iteration 2, after we reassign the lower level capsules based on their fit, some of the class capsules lose submorphs and some gain support and become tighter as well. So we did a refinement and our arguments boosted. Now we do another EM algorithm, EM step, and we settle correctly on the chalk capsule with a tight active cluster. This shows another example for a human image. Interestingly, after the first step, animal and human get boosted. This indicates that their part-whole relationships are quite similar. We also tested capsule networks on their ability to generalize to new viewpoints. So we trained only on 1/3 of available viewpoints in the NORB dataset. At test time, we asked it to extrapolate to novel viewpoints. We compare capsule network results to a baseline convolutional neural network. And capsules obviously have significantly lower test error rates on these tasks. So currently, so far, at each step of training and inference, we are transforming and then running a loop to figure out the centers. Can we do this without iterations for the sake of efficiency, for example? A new idea is to bypass the fitting and leave it to an MLP to figure out the capsule coordinate frame. Then the top capsule transforms their coordinate frame and gives prediction for the bottom capsule coordinate frame. The predictions are depicted via crosses in the lower capsule representation space on the left. Take these predictions as the center of the Gaussians in a Gaussian mixture model, so the crosses. Each of the parse capsules, the disks on the left, picks the closest prediction as its parent. We learn the transformation and the MLP by optimizing the lower capsule, so the lower capsule, not the class capsule, the lower capsule coordinate frames under the predicted Gaussian mixture model, the mixture model that we got from the crosses or the prediction. In addition to eliminating loop, now this section can be changed without supervision. So let's take a look at the task that we started with. We color the points based on which parents they choose in the CapsNet. We see that the CapsNet finds the true underlying common pattern in most cases. We compare our models with a baseline which has a decoder with several layers rather than single matrix transformation. All other aspects are kept the same. It's just the decoder. We compare the percentage of points that don't get grouped together. So if, for example, 4 points that belong to a square, now one of them is not grouped with the other 3, then that's a failed grouping. We see that the capsule autoencoder is significantly better at finding the underlying pattern without supervision. Assuming that viewpoint varies between images, capsule autoencoders can easily disentangle viewpoint from shape. During the past 40 minutes, we covered motivation for capsule research, introduced basic elements of a capsule network, talked about figuring out arguments and assignments. We have learned why finding arguments is advantageous to summing up evidence. Also, we have learned how to get smart sparsification and scene parsing via assigning parts to objects. We also gave 3 examples of practical techniques for accomplishing these functions. And that's about it. Thank you. Now let's take a look at the questions.
Hi, everyone. Can you hear me?
Hello, Sara.
Yes, hi.
Hello, welcome back, everybody. I'm honored to have Sara here to answer your questions. So if you, Sara, allow me, then I will read questions out loud for everybody, including you.
Sounds good. Yes, sure. Thank you.
Okay. So the first question asks by Babak, which asks that each capsule finds its specific pattern in the input data, image or previous layers output using convolutions. But conv layers are not able to find many transformations like rotation. So how the capsule can find a specific pattern?
So only the primary capsule, like the first capsule layer, is connected to the image with convolutional layers. And the idea is that the capsule, the primary capsules should encode the position of the parts, not exactly the transformation, but your concern is correct that we are using convolutional networks, but uh, I think convolutional networks, but themselves are not like, it's not that they are unable to handle rotation. It's just that when you have a fully convolutional network without any capsule layer and you optimize that for supervised classification, it will learn to ignore the viewpoint, become viewpoint invariant, and ignore the rotation, just attend to the texture because that's the best cue and easiest cue for it to do the classification. But if you force a couple of convolutional layers to extract position from the image, they are able to do that. And people have been using convolutional layers even for 3D graphics and other graphic applications that specifically work with position.
Mm-hmm. And in these scenarios, I guess that the rotation is a label for such a training, right?
Yes, in those scenarios, they directly supervise with rotation. Although one thing that we make sure that we didn't have was stride or pulling in our convolutional layers. Because if you have a stride or pulling, then you cannot, you will definitely lose information about the position in the image.
Okay, great. Then the next question is about the vulnerability always. There is kind of these questions like against adversarial attacks because they are so hot topic these days. So are capsule networks robust against adversarial examples? If yes, how and why?
So in our EM capsule paper, we had some preliminary adversarial robustness experiments against typical, like the FGSM and I think PGD, so the first 2 easiest ones. And it seems that at least when we tested that the capsule networks are more robust to especially white box attacks. So the attacks that use the gradient of the network to do that. But recently there was another paper that was like suggested a new attack, and they also tried it on capsule networks, and it was as vulnerable as other CNNs. So there are some robustness inherent in it, but it's not that it's fully adversarially robust. And like amount that it's more robust is very small.
Okay, thank you. And another question by Heidi asks about conceptually how the capsule networks can understand the part positions from another view, even if it's not seen.
So if they are able to extract each part position and work with the numbers, so it's about computer graphics. That's exactly how graphic artists generate animations. So they specify the relationship between the parts in the image that they are rendering, like the face, the roof, etc. And then whenever they want to rotate the image or take another view of it, they don't need to change those relations. They just change the input and the output automatically changes. That's how capsule networks ideally can do that as well. Like if the position of the eye is 1 and 1, and you know that you need to multiply it by 2 and 2 to get the image, then if it detects the eye at 4 and 4, 8 and 8 is still the right position for the object. And again, these viewpoint generalization that we have, it's just that it's better than CNNs. So it's not like we solved the issue, and the version that I've presented here is a completely viewpoint equivariant. There are other versions of capsule networks that they have also fixed the bottom part from image to primary capsule to preserve equivariance and the spatial positions with specific group operations. And those ones can preserve accuracy even when the image is rotated. So for example, when we say we have better viewpoint generalization, it just means that, for example, if the accuracy on norm itself, the test error is 1.4, but when we do the viewpoint generalization, the test error is 12%. So it means that it's not a completely viewpoint equivariant, like it's losing 10% accuracy because of the viewpoint. But the thing is that CNNs lose 20% accuracy. So the fact that we are better is enough.
So I guess this is aligned with the question of Amri. He asked about what's the what if instead of capsule network we use traditional CNNs with augmentation data which are rotated? Which one is better?
So that's exactly what other methods essentially do to get very good results, which is data augmentation. We argue that that's very inefficient to try to do, especially for unsupervised networks. Like that was the state of the art, at least last year, and I think it's still state of the art to augment the data and pass it through the network and do contrastive learning on the last layer to train. And personally, when I played with it, try to replicate their baselines, like you need to do millions of iterations of data augmentation to get the same results. So it's your question is similar, but to say, so the relation that capsule networks have with CNNs is exactly what CNNs have with fully connected networks. So ideally, you can have a fully connected network and augment the data by translating the image all over the place and chain it a lot more. And the fully connected network should learn the CNN structure, because you can exactly define the weights in a fully connected network that would replicate a CNN structure. So fully connected networks can be as good as CNN if you augment the data enough, but still you would rather to play with the CNN because you don't want to waste that much energy, the augmenting.
Yes, okay. The next question asked by Reza is that what's the relation and difference between disentangled representation learned by CNNs and CapsNets?
I'm not sure what are disentangled representations learned by CNNs exactly. Like, is it referring to a specific paper?
Maybe Reza could ask more details about this. Maybe next question by Reza is regarding to this. Does capsule network robust to texture bias? So that this kind of maybe representation inside the layers he's addressing to.
I see. So capsule networks currently ignore the texture, but they're not very good at doing that. So the versions that I presented here actually struggle. So on images that have that are very texture heavy. So they don't have really good results on the text. They try to ignore it. So they should not be biased with the texture, but the presence of any texture by itself reduces the performance. So for example, in the unsupervised case, one thing that we did was pass the image through Sabour filtering to remove the texture and just pass the edges through the network. We are working on a newer version of the capsule networks that would be able to handle texture and background. And the most recent version would be robust to texture bias. But right now, the capsule networks, at least the ones that I presented, I think they suffer from texture.
Okay, cool. So stay tuned for the next publication. And then the next question is by Mohammed. He asked for, in many papers, results show dynamic routing is so complicated and should be optimized. Is that right?
So what happens in practice is dynamic routing is memory inefficient. So like I've put the code on GitHub. You can download it. There is the MList checkpoint that gives you 21 wrong examples, but you cannot scale it to ImageNet images. And the reason is that, like, if you use an image that's 256 by 256, you will get out of memory. So that's why we designed the stacked capsule autoencoder, where it's not doing the routing anymore and it's learning a network to do the routing essentially. And it's able to process images that are 128 or 256 now.
Okay. So maybe I ask a question right here. That reminds me, this dynamic routing reminds me of somehow pruning such networks. Is there any relationship between this? Because as the visualization was, I was watching the visualization, and that reminds me of this kind of pruning unimportant weights or routing important weights.
Yes, exactly. Dynamic routing is a sort of like a smart dropout or a pruning technique. The main difference that it has with typical pruning networks, pruning methods, is that they're usually static. Like you do it you train the network, then get rid of the weights that are unimportant, and that's it. That's your network during the test. So it's a fixed set of connections. Whereas dynamic routing decides the connections for each image, even during tests. So that smart dropout is essentially a nonlinearity that happens during test as well.
However, it's not efficient regarding the hardware requirements, right? So you need a lot of requirement.
You need more memory, but that's mainly because of TensorFlow. I would say, like, the main reason is that we are not able to use convolutional kernels, like the kernels that are provided in CUDA, essentially, because we need to sum up the incoming predictions weighted, like we need to get a weighted sum of incoming predictions, whereas in convolution, you just sum the multiplications. So we need to get our own convolutional kernel. Like if you do the typical CNNs in the TensorFlow API rather than using CUDA kernels, it will be exactly the same.
Okay.
And we have talked to NVIDIA engineers, and they said that if they implement the kernel, it will be 100 times more memory efficient. The reason is how we implemented it, but not structurally, because you can view 3 layers, 3 routing iterations. You can unroll it and view it as 3 convolutional layers. It's less than like the amount of computation and the memory that it requires. It's like, assume that you do it 3 times, one after each other, like you have 3 layers. And we have ResNets that have 50 layers, but the capsules have 10 layers. So if, like they have 4 layers. So if you, even if you not do the routing and unroll it, it's like a 12-layer network. So it's less than ResNets still, but the reason that it blows up in memory is that we are doing the convolution inside TensorFlow rather than inside CUDA kernel. So TensorFlow keeps, or it's the same with PyTorch. They keep several copies of all the operations to be able to backpropagate and expand and everything.
Okay, cool. And this question is asked by Babak. So last year, a very interesting paper published on gauge equivalent convolutional networks. They use convolutions for finding patterns even in curved spaces. Capsules are considered next generation of deep neural networks. So can capsule nets used in the way like gauge equivalent convolutional networks?
I don't see why not. So they should be able to adapt it for capsule networks, and there has been several group equivariant convolutional networks, not exactly gauge equivariant. So there's nothing inherently wrong with doing that. So you can adapt that for capsule networks as well.
Okay, cool. And the last question is asked by Hadi. It seems that we need a big number of capsules when we have different objects like classes. So with a lot of differences and with a lot of differences in appearance, could you explain the generalization of this method for complicated scenes and huge number of classes?
So if you compare it to a neural network, a CNN, the equivalent would be to replace each neuron in a ResNet with a capsule network. So if you want to get ImageNet accuracy, you probably need a network that's, and assuming that, for example, 16 dimensions is enough for the capsule to carry the meta information like position, then you would need a ResNet that's 16 times wider, and it will be the same. Ideally, like I think it would be the same. So yeah, that's always what I had in mind, that you can take a ResNet and just replace each neuron with a capsule, then it would be the same. But you can argue that 16 times wider ResNets are too much. But the number of capsules resonate with the number of neurons in a simple CNN.
Okay, great. Thank you, Sara, again for your great talk and attendees for the great questions. So with this, I will finish this session. Thanks again, everybody, for attending today's sessions.
Thank you.
Thank you. Bye.
Bye.